podcast is brought to you by LMU Munich.
The nature of science is the title. Here's the outline. I mean, giving a talk in this institute is probably not shocking for anyone that the talk has a structure, right? And an outline, and it's systematic. So I'm asking a question, and the question is, what is science? And then there will be some preliminaries, and I will even answer the question. That, again, at this place particular, will not be a big surprise that philosophers ask questions and also answer them. And even then explicate the answer, make the answer clearer, qualify it, make conceptual clarification, and of course then justify the answer. So this is a pretty dry systematic thing. You have a question, and then you discuss the question in a historical perspective, and you discuss the question in a systematic perspective. Then you answer the question, then you have to do something with the answer, you explicate the answer, and then to justify the answer. And this here, the comparison with other positions, is not a remnant from my continental background. No, this is also an argumentative step. It's not just comparing and then looking, mine is much nicer or something. But you will see that this will be an argument, because I will show you that these older positions then in some sense will support the answer I'm giving here. I'm just not saying they're just false, but in a sense they support what I'm doing. And then very, very traditionally I put the summary at the end. Okay, so we start with a question, and here are the historical preliminaries that will show you why it makes sense to ask this question, what is science, even today in 2011. And the historical preliminaries consist in a phase model of the answers that have been given to this question. And of course the historians won't like that. That's fine with me, and they are right, but I'm a philosopher, and we philosophers sometimes tend to have something like a schematic history that does make sense, not as history, but as something which prepares a certain question. That's what I'm doing here. So the answer is, the answers that have been given in four phases is antiquity until the 17th century. The answer to the question about what is special about scientific knowledge is that it is certain knowledge, and the certainty of that knowledge is established by proof. That's the standard story of antiquity and the Middle Ages. And then we have a second phase from the 17th century to the second half of the 19th century. And again, we have the same scientific knowledge is certain knowledge, but the means by which the certainty is established have been taken in a wider sense. They are now established by the scientific method or the scientific methods, which is a very, very nice ambivalence, but I'm not going to talk about it. And then in the second half of the 19th century until the last third of the 20th century, a new insight about especially scientific knowledge in the sense of natural science has emerged, namely that scientific knowledge is fallible knowledge, but still the idea was that this scientific knowledge was established by scientific methods, and then the drama unfolds in the last part of the 20th century until now, namely the idea that the question what constitutes science, that this cannot be answered by a scientific method. It's the dissolution of the persuasion of science as a strictly rule-bound enterprise induced by historical studies. And that, of course, provokes the question, what makes science special? What is special about it? And you see that even better when I give you here a little graphics. There you see we start here in antiquity with deductive proof and certainty. Then we keep certainty and replace deductive proof by scientific methods, which is of course a generalization. And then certainty disappears, but we still have scientific methods. And then here the catastrophe emerges, namely that scientific methods disappear and only fallibility remains. So what is special about science? Fallibility. Wonderful, right? So this is a catastrophe, and who are the people who should be competent and willing to take the responsibility to answer the question, what is science? Well, philosophers of science. What have they done within the last 20 years about the general question, what is science? And the answer is very simple, nothing, or almost nothing. So I think it's a really topical question, because we philosophers of science should be able to give a convincing answer in all generality about this question, because physicists can't do that, and literary theorists can't do that, and mathematicians can't do that. It's really the job of the philosophers. That's the fundamental question in philosophy of science. Okay, is that enough of legitimation for the question? Yes, thank you. All right, now here we come to the systematic preliminaries, because in philosophy it's always worthwhile, before answering a question, to discuss the question and really trying to understand what the background, the systematic background of the question is. And I make a few remarks here. I do understand this question in the sense with the concept of science with the largest possible disciplinary extension. In English, one could say all fields of research. German has a word for that, Wissenschaft. So everything that's taught at the Ludwig-Maximilians-Universität in München, that's Wissenschaft. Okay, it may be bad science or better science. Well, it's all excellent here, more or less, right? Yeah,
I hope you would say that.
Yeah, sure. I mean, we from northern Germany, we see that, of course, immediately. Anyway, so it's all Wissenschaft, and so the task is rather asking the question, what is science in the sense of Wissenschaft, is, of course, almost suicidal, and because it's a rather large question, and I give you a quantitative measure for the largeness of this question. So, but that's at least the aim. And then the focus of this question is science in the sense of scientific knowledge. So I'm not discussing mainly social aspects of science or economic or military or something like that, but it's really scientific knowledge. What's special about scientific knowledge? Then the main contrast, and here now I'm deviating from the tradition of the 20th century in a very important way, and one should really keep that in mind because otherwise you are misled. I am not asking the demarcation problem. I mean, you know the history of the demarcation problem. It didn't lead anywhere. I will have an answer in the end, of course, also for the demarcation problem, but it will be a very complicated answer. And I'm starting this other sort of enterprise here, that my main contrast in the question is everyday knowledge. So when I ask what is science, I don't have in the back of my mind, in contrast to pseudoscience. That is how the question was always asked in the 20th century. But I'm asking the question, what is science, in contrast to everyday knowledge? And that's a very different question. So you may see that whenever you ask a question, a what is something question, usually you have something and you have contrast in the back of your mind. And if you want to deal philosophically in a responsible way with a question, you should make that explicit. And for me here, it's absolutely essential to make that explicit. So my main contrast to everyday knowledge is not pseudoscience or metaphysics in any sense, as Popper would have it, but it is everyday knowledge. And you'll see that later very explicitly. Furthermore, I make no metaphysical presuppositions, and I'm saying that in the following sense you are misled by the title, the nature of science, which would be, of course, an essentialist answer in terms of necessary and sufficient condition. And as my colleague and friend Matthias Frisch, of course, immediately considered as the possible answer that I'm going to give, namely what is science in terms of necessary and sufficient condition, and I'm not going to do that. Okay, so I'm asking the question, what is science, but I'm not answering the question in that way. And then you ask, oh, what sort of answer are you going to give us? You'll see. Wait a minute. Okay, so what I mean is I'm asking the question like a child asks the question, without metaphysical presuppositions. And what is science? Just tell me what science is, damn it, you know. And what an appropriate answer is depends, of course, on certain factors. It doesn't have to be in terms of necessary and sufficient conditions, even if Plato wouldn't have been satisfied with another answer. But thanks God, the 20th century is behind us, we've learned something, and I'll show you how I treat that problem. So no metaphysical proposition is completely open. It must be a convincing answer, what is science, and then we'll see what properties the answer has. And then, again, something, again for Matthias, because he said, oh, you're giving us very sharp boundaries, right, of what science is and what bioscience is not, and that's exactly not the case, because if you look at science, especially there in the natural sciences, there aren't really sharp boundaries at some places. So for instance, if you look at earthquake engineering, which is a discipline that's well established, especially in Japan, but also in Harvard, it is not the engineering of earthquakes. Right? Don't misunderstand that. It is the design of buildings that are earthquake resistant. Right? That's earthquake engineering. It's quite misleading, okay? So earthquake engineering, and if you look there, then you find, for instance, in the engineering departments, say in Tokyo University, you find that they think about earthquake-resistant designs for buildings. And for instance, a very interesting thing, what they did there, they built a bank building with 12 stories, and that bank building is a bank at the one hand, at the same time it's a scientific experiment. It's full with sensors, you know, and measuring instruments. It's a new design, and they're waiting for the next earthquake, and then they measure all that stuff, and the people down there lose their money with the bank. Okay, so you have here a transition between design of a building, so research and development is something where there are no sharp boundaries between scientific stuff and really applications. And another thing you will not know is that there's a science of chocolate. There's a volume by the Royal Society of Chemistry, The Science of Chocolate, which appeared in 2000. But it's going back. I found a diploma thesis from 1953 done in the DDR, in the German Democratic Republic, on the science of chocolate. And there's also a scientific side, namely the principles how to produce chocolate. Chocolate is a very, very complicated substance. It's really complicated when you look at it. What chocolate must have, the properties you want to have of a good chocolate. So there is, of course, and I did that. I went, for instance, to Lind and Sprüngli, to the web pages, and there you see they have a research department and they have a department for developing new products. And there's that, of course, there is no sharp boundary. So when we have a theory, what science is, that theory would be bad if it had sharp boundaries everywhere, because the real thing we are trying to describe here doesn't have sharp boundary, and that, of course, an appropriate descriptive theory of science should reflect that gliding transitions here. Okay, so don't expect sharp boundaries everywhere. So, and here's the answer that I'm going to explicate and defend, and it's a seemingly very simple answer. It says scientific knowledge differs from other kinds of knowledge, from everyday knowledge in particular, primarily by being more systematic. Okay? Systematic, here's the term. Scientific knowledge differs from other kinds of knowledge, from everyday knowledge in particular, primarily by being more systematic. That's the thesis. Okay, now some qualification before I continue. Note please that the answer is comparative in character. That it doesn't imply that other kinds of knowledge are entirely unsystematic. So for instance, if you want to know how many people are in this room, you count, and from that you won't get a degree from Hannes just in mathematical philosophy. It's just our everyday knowledge that we know counting is a cultural technique, and it's entirely systematic when you count here one by one. So also everyday knowledge may be systematic, but the claim of the thesis is that scientific knowledge is more systematic. Okay? The second to be noted here, which is implicit, is not explicit, therefore I'm saying it, more systematic refers to knowledge about the same domain. Right? You must not compare, according to this thesis, knowledge of different domains, because there you may find scientific areas which are not very systematic, and you may find not scientific areas which are extremely systematic. So I looked into, for instance, the international system, how one identifies serial killers and serial rapists. And there's a system that was introduced in the mid-90s by the Canadian police, and that's a very complicated system, extremely systematic. They have 500,000 cases now, crimes, singular crimes, and each singular crime is described by several hundred variables, and then the computer then tries to correlate it. It's extremely systematic. What I mean here is just imagine what you do when you see someone and you form and a person you haven't known, so most of you, with me, you saw me, and then within a few seconds, 30 seconds, a minute, you had a certain image of me, right? And now you're exploring who is that guy, and so on and so forth. Compare that with the techniques if you apply to some firm, say Siemens, to a higher management position. They send you typically to an assessment center. And at the assessment center, you stay there for 10 hours or something, and they run 5 or 6 different tests in a certain order, blah, blah, blah. What you see is this is a very systematic procedure, what they do, and the subject matter is the same, getting to know someone. And our everyday techniques are less systematic than the scientific techniques. That's the idea here. So it refers to knowledge about the same domain. And furthermore, the answer is not immediately applicable to areas where science is the only game in town. In front of mathematicians, of course, I have to say that because that's the obvious counter move. Oh, what's the everyday knowledge of black holes, for instance, or the folding of proteins into their three-dimensional structure? Of course, the thesis is silent about that, and it would then say, oh, okay, it's not scientific. I know it, I can add a few epicycles, and then I can deal with these problems too, but it's not very interesting. But if you want to know it, I'll tell you in the discussion. And then very important, of course, the answer is primarily descriptive and not normative. And everyone knows, of course, the difference between descriptive and normative. The point in philosophy that's most important about this distinction is that the argument for a descriptive thesis are always very, very different from the arguments for a normative thesis. And that will cost much effort later, but it's very important to see this is meant to be a descriptive thesis, not normative. I've put in the word primarily in here because one can tease out certain normative not consequences in the literal sense, but certain implications, roughly speaking. But that's not the main aim. The main aim is descriptive. I'm describing the real sciences, the real Wissenschaften. Okay, so of course the question that arises now is, what does systematicity mean? And that is a little frustrating because the term systematicity is not a philosophical term anywhere. You don't find it in any encyclopedia. You find, of course, in German encyclopedias you find System, but you don't find even System, rarely in English encyclopedias. And the word systematicity has had a career now for the last 15 years in linguistics, and it means something completely different. There's even a book by the title, Systematicity. So when you Google systematicity, you must go to number 150 or something until you find the name Hoyningen associated with it, but you find the linguistic stuff with it. Okay, so the question is, what does systematicity mean here? And here's an interesting observation which I have discussed with many people, because I think this term systematicity, or this concept of systematicity, has a peculiar property that I have not seen analyzed in any philosophy of language. And that's the following, that in order to deal with this concept, to make it, to explicate what it means, one has to have two steps. And the first step is to make it more precise and more concrete. And you will see in a moment what I mean. This is not the only concept. It's a concept where in the abstract you cannot say very much about it. And you must say in which context you want to use the concept. And then you can say more about what it means. And there are other concepts as well. I use the concept as Verfeinerung, refinement is a similar concept. Just think about when you want to explicate or explain to someone what is a refinement. Then you can say, okay, what is a refinement? Yeah, you have something coarse and you make it finer. Well, now it's already circular, it's not very nice. Okay, you have something coarse and you improve it in some sense by looking closer or whatever it is. No, I mean, this is almost nothing. Once you say, I want to refine the properties of a certain optical apparatus, you know fairly well what to do usually, right? You've got to adjust the lenses a little better, take bigger lenses, and so on and so forth. Or you want to refine a sauce when you cook. You know exactly what to do. Usually you add milk or cream, right? And you let it simmer a little and so on. Or you want to refine your writing style. Okay, get away get to the active form, away from the passive form, use less nouns, more verbs, and so on and so forth. So whenever I give you a context, I can tell you what a refinement is. But on the abstract level, one can say very, very little only. And this is an observation, and that is the same with systematicity. So I need two steps. I can make it more precise on an abstract level, and that's the same with the refinement. You know, one can look for contrast, and that works, but it doesn't lead very far. So for instance, contrasting concepts to systematic are something that's purely random or accidental, something that's arbitrary, unmethodical. Oh my God, I did the worst thing in the world here. I do have all these things. I'm sorry. Okay, unmethodical, unplanned, unordered. Being systematic, that's one can say on an abstract level, is something like it embodies some kind of order. Yeah, that's almost nothing, you know, some kind of order. What does that mean? It's almost empty. You can't say much more. So we need a second step. We need contexts in which we want to use the concept. And what I'm doing next is that I give you these contexts in which I want to use the concept of systematicity with regard to science. And the context you will find, hopefully at least, quite plausible. It's the context which then differentiate the thesis that I propose to you, namely in 9 subtheses. It says then, scientific knowledge is claimed to be more systematic than other forms of knowledge in 9 different dimensions or 9 different aspects of science. And you will see quickly what I mean. So the claim is then scientific descriptions are more systematic than everyday descriptions. Scientific explanations, then scientific predictions, the scientific defense of knowledge claims, the critical discourse, then epistemic connectedness. You don't understand that here. It's fine. I introduced the term. An ideal of completeness, knowledge generation, and the structure and representation of knowledge. These are, to repeat, 9 contexts or 9 dimensions of science. And the claim then is that the general thesis about the higher degree of systematicity is in truth 9 different theses. Namely, the claim that in these 9 different dimensions, science is more systematic than everyday knowledge. And the meaning of the term systematic varies here, and I'm going to say more about that. Here are some remarks. The more concrete concepts of systematicity, think of Verfeinerung, refinement of your writing style, refinement of a source, refinement of an particular apparatus. The term refinement means something else in all these different contexts. That's the same here. The more concrete concepts of systematicity, corresponding to the 9 dimensions, exhibit only family resemblance among each other. If they didn't, you would find the necessary and sufficient conditions at the abstract level. And so it's a sort of confirmation, because you don't find anything, then of course you may ask, oh, that may be due to this funny nature of that concept. They are sub-concepts in concrete context, and they are connected among each other by family resemblance relations, in the Wittgensteinian sense, of course. So the more concept, they exhibit family resemblance, and it's becoming even more complicated, because also within one single dimension there are different concepts of systematicity, conditions mainly by different disciplines and subdisciplines, and again they only exhibit family resemblance. So I give you an example. If you look at descriptions in the historical sciences, and we take the subdiscipline of the history of mentalities, right, which is especially in France a very active form of history, the history of mentalities. For instance, the history of childhood. What was a child in France, say in the 17th century? How was a child? How was a child seen? You know, that belongs to the history of mentalities. And compare that with the economic history. Say also in France between 1650 in rural France, and you do economic history. Now, if you look at the descriptions you are going to give, and you make descriptions more systematic in economic history, that typically means that you have more quantitative variables, right? You have more data, you collect more data, you've got more aggregated data, and then your description of the economic development in France in this particular time becomes more systematic by having more variables and more numbers, right? In the history of mentalities, it's usually not at all a quantitative affair. It's a question, for instance, you become more systematic when you, say, add certain developmental theories from developmental psychology, and then you add that and then try to systematize certain data you have from many, many different sources what people use there. So the story is even within one discipline. The concept of systematicity regarding just one dimension again, only descriptions, may vary. And that means that we get as many concepts of systematicity as we have disciplines and subdisciplines, and that times 9, because we have 9 dimensions. And I'm going to tell you the number that results from that. It's a large number. It's an unbearably large number. And the consequence immediately already from this sort of architecture of the whole theory is that systematicity as a hallmark of science does not claim a rigid, unique structure of the sciences, because it's a web of different concepts of systematicity connected among each other by family resemblances, and it's even more complicated, all that moves in time. We've got a historical development. So you have at one time, say, if you look at chemistry, for instance, you have at one time a chemistry before the 19th century that was almost purely quantitative, and after the 19th century, or in the 19th century, it becomes quantitative. So the concept of systematicity changed. So we have, and this is just what we have here. I mean, the whole system of the sciences is a big, big, big thing, and it develops in time and changes. And a theory of science that asks what is science, of course, has to confront that, and that's, of course, difficult. It's complicated, and the question is whether on the level of philosophy one is able to say something meaningful about this historical entity, or whether the historians are the only ones who can say something. Well, I think one can say something. All right, so this is just the consequence, and here we have now the following problem, that the further elaboration and justification of my answer would have to show that all sciences are more systematic than everyday knowledge in all 9 dimensions. Okay? And now, how many sciences are there? Well, unfortunately, there is no discipline which existed once called Wissenschaftskunde. You know, like geography, there is no scientography. Geography, the old geography told you what is on the earth. You find the countries and the continents, and they tell you what people live on and what the mountains are and the rivers and so on. Just make you familiar with that. Now, there used to be eine Wissenschaftskunde, like Erdkunde, that's in German the same word, it's the same kind of work. A Kunde means a very, very modest descriptive enterprise. Mineralienkunde and things like that. This is in German this very modest term, and we don't have that. So if you want to know simply how many sciences are there, what are these sciences, also you won't find a single book, because there is no science that does that, unfortunately. So what are you doing? Well, you look where people try to classify sciences, and you can go to very, very many different sources, and it's a mess. Even the terminology is a mess. You don't find a single terminology. People speak about, say, disciplines, subdisciplines, and fields and subfields, but if you compare other authors, it's a real mess. Now, I give you the figures. The figures is that counting disciplines leads always to something between 200 and 600 disciplines. Right? That's just the disciplines. Counting subdisciplines is something like 8,000. Right? That's the best guess I have. 8,000 subdisciplines, right? Everything, humanities, right, and natural sciences, engineering sciences, and formal sciences. So we are dealing with something that's the cosmos, but nobody knows, nobody knows. Only one publication makes the guess of 8,000, I think 320, so that's the order of magnitude. And I have 9 dimensions, so we are dealing with the 72,000 theses that I have to argue for. And I'm glad I've given a full week for this talk, because then I can do a little. But of course, that is the price of a descriptive enterprise. That's the price. The thing I want to describe is very complicated. It develops in time. And I want to describe it somehow in general terms. And I have to deal with something like 10,000 or 8,000 subdisciplines. That's the price. So when I say something general, I have to argue with respect to every single damn subdiscipline, right? Or field, whatever it is. And of course, that's difficult, but one has to confront that. And what I'm going to do is, in order to argue then my thesis in these 9 dimensions, I will have to use examples, and the question is, of course, finding nice examples. I'm not saying I'm finding representative examples, because that would be cheating. To show that something is representative means that you see the whole variety, right? And then you say, I look at that, okay, this is a representative one, but I can't do that. Nobody can, unfortunately. I'd love to have a Wissenschaftskunde that would do that job for me, so I had to all do that as a pedestrian. Okay, so my next step is then, and also for some aspects I can refer to standard results in philosophy of science, and some of the dimensions are not relevant everywhere. For instance, in mathematics itself, there are no predictions. Also in many historical disciplines, there are no predictions. But I took the predictions after some hesitation on board. At any rate, so my next step is then to justify the answer and to be very precise at the same time, but I'm not going to do that really explicitly. I must, for every single discipline, also make explicit what the term systematicity means there, right? Because it changes from subdiscipline to subdiscipline and from dimension to dimension. I have also 72,000 concepts of systematicity. I'm sorry, I haven't invented the system of science. It's just there, and it has, unfortunately, these properties, which makes life so difficult.
Jeff, can I ask you a clarification question about you want a relational notion of systematicity. What are the relata? Are they theories or are they...
It depends. It depends. It depends. No, it depends. No, it depends. It's descriptions. Look, wait a minute. You'll see it because I'm doing it now. Now I'm running through the 9 and I give you examples, and believe me, I do have many more examples. I can only do it, I've worked on this thing now for 12 years. I sent my book to the press, and it was rather hard, believe me, to find all these examples in these many different fields. So, systematicity of descriptions. In the classic formal sciences, mathematics of course, you have an axiomatic description of a domain of inquiry. This is of course in some sense the highest degree of systematicity that you can reach. You write your 4 independent axioms, and they cover the whole field. That's the description. That's all in there. Extremely systematic. Just imagine you ask someone in everyday knowledge what are natural numbers. Then this person will say, oh, this is 1, 2, 3, and so on. And you ask a mathematician, he writes down piano axioms and says, yeah, in principle, that's it. Okay? So, and you see that this is the difference between the systematicity of the description in mathematics, and it's, of course, obvious here. Then, one thing that many different disciplines use is classification. It's one of the means how you can improve the systematicity of descriptions. And as you know, I mean, mathematical objects are classified: biological species, minerals, chemical elements and compounds, languages, form of government, literary genre. Just to give you a few ideas what is happening here. Biological species, we're talking order of magnitude 10 million, right? Chemical elements and compounds, we're talking order of magnitude 65 million, right? Languages, order of magnitude 5,500. That comes, the hierarchy in biological species is now 30 levels. There are different systems, one with 29 levels, another one with 32 levels of hierarchical. This is very systematic, right? Where you put all these 10 million species in. Language is very interesting. It's it's a hierarchy of 5 different levels, and there are 5,500 languages. Between 2000 and 2005, 200 new languages were discovered. Between 2005 and 2010, several dozen languages disappeared. So it's a living thing, right? Languages on Earth are a living thing, historical entities. So in order to bring order, just to describe that, science has to be extremely systematic, and classification and hierarchy is one of the means that you find. So what you see here, I'm using just one sort of gimmick that the sciences use in order to increase systematicity, and you see, of course, I can kill here thousands of disciplines or subdisciplines with one stroke, right? Because classification is a very universal means. You find the same also in history. The systematicity in history, you have the temporal analog, which is periodization, and you find periodization in many disciplines, again in Egyptian history and in geology, and of course in general world history and so on. And it's also some way in order to make descriptions systematic. So then furthermore, it's also almost trivial, but it's worth having a look at it. The quantification of descriptive statements is an extremely good means if it works. If it works, to the social scientists, in order to get higher accuracy, just remember when you describe the temperature so our normal human temperature it's between extremely cold and very hot. And then if you ask how many words you have in order to describe that in everyday knowledge, you will have 20 perhaps, or 15, and they are not well ordered. Just spend €3 on a thermometer, right? And then you get immediately 600 well-ordered descriptive statements, right? It is minus 29.5, right? Until from minus 30 to plus 30, 600 different well-ordered. Isn't that more systematic? That's the power of quantification. Why do the scientists love quantification? Because, among other things, they make descriptions so wonderfully systematic. Okay, that's not the full story. Then furthermore, of course, in all the engineering sciences and in many natural sciences, you use empirical generalizations in order to describe things. They presuppose adequate classifications, otherwise the generalizations won't work. And something else is, I mentioned it already, periodization. It's in all historical disciplines you find it. I didn't find a single one where it wasn't used, some sort of periodization. But you also find it in developmental theories. If you look at life cycle theories in psychology, There you find there are something like 10 life cycle theories that describe the normal development of a human life from newborn to toddler, and they have different stages, and that's of course something by which you make descriptions systematic. That is what the sciences do. Okay, and then we have historical descriptions, namely telling stories. They have also an explanatory role, but they are also descriptive, and they have the same structure as everyday stories, but they are more disciplined in several dimensions, and more disciplined is of course then more systematic. So this is a very quick view, which must be elaborated, but I must go through all the 9 dimensions in order to show you what I mean here by the systematicity. Now let's look at explanations, the second dimension here. And of course, explanations by empirical generalizations is something we also do in everyday knowledge, but we do it in science as well, much more controlled. We are much more careful in science when we do that. We have explanations with recourse to causal theories, and we get, of course, unifying explanations that are, of course, more systematic because, you know, just you have the resource, an extremely powerful resource when you use quantum theory or gravitational theory in order to explain phenomena, and, of course, this brings much systematicity into the explanations. In the social sciences, for instance, we have explanations of actions with recourse to intentions and belief, and they have the same structure as in everyday life, but are more systematic, and this also holds for the historical disciplines. I had, for instance, a look in the historical disciplines. As a case study, I looked at the scientific explanation of why Truman dropped the atomic bombs on Hiroshima and Nagasaki. And it really boils down to the same, what we say, why did you come to Zurich? And then why did you come here to Munich? And then I say, well, I wanted to come here and give a talk. And then I thought it would be good to come here, right? Intentions and belief. And it really boils down. This is a complicated question, this Truman decision. And I looked at it in quite some detail, including the diaries of Truman, which are on the internet. And it's a very complicated story, but the question is really the only question. Why did he do it in the sense, what was his intention? And why did he believe that the dropping of the bombs exactly on Hiroshima and Nagasaki really were the best means he knew in order to realize his intentions? It's exactly the same, but there are dozens of books just on this question about the decision of Truman to drop the bomb. And it's a very complicated story, but you see the structure of the explanation is really the same, but it's extremely more systematic in the historical sciences. And here's something else, which I'm not going into details. I looked in the literary sciences as well, and this is very interesting because we have, in literary theory, we have texts that are fictional. And the fictionality of the texts gives rise to the possibility of different sorts of explanation, and this difference of explanation is sometimes expressed as the pure poetological difference. And when we look at it, it's something that the literary theorists do, something that we even do sometimes as lay readers of novels and poems and so on. So it's again something they do it much more carefully. They write full books about the poetological difference. So we find that also here. And here you see, of course, I'm now here really deep in the humanities. That's not a science in the English sense of the word, but it really belongs to the humanities. But I think that the thesis applies there too. That's at least the intention. And of course, explanations by models, they come in thousands different kinds. I mean, just explanation by models would fill, I think, at least 5 volumes probably if one looks. But it's, of course, again the case. We also, in everyday explanations, sometimes use something like models, but it's quite clear that the sciences use them much more consciously, much more systematically. Okay. And, reductionist explanations. Some people don't like them. I don't care. But there are reductionist explanations, and you find them all over the sciences and humanities. You find them in linguistics, and you find them in biology and in physics and in chemistry and in wherever you look. You find them. Whether they are the last word or not, I'm not going to discuss. And they are, of course, extremely systematic because it's an explanatory strategy where you know exactly what you're doing. You look at the parts, you look at the interactions, and then you explain the properties of the system and the dynamics of the system. And that's, of course, we also do that. Every mechanic does that. When you come and say, oh, my car doesn't start, then the first thing is it electricity or is it gasoline? And then he continues there systematically. But it's something that's, of course, brought to a high degree of refinement here in the sciences. Okay, where are we? Oh, right, okay. Now, systematicity of predictions, I'll make that a little faster again. There are many, many, many different ways in the sciences. Direct recourse to deterministic or probabilistic empirical generalizations or theories is the straightforward way to do it, and you use that in astronomy, nuclear physics, many other things, and then of course models, simulations, time series, statistics. I looked at especially at economic predictions. You find just 10 years ago a 2-volume encyclopedia of predictions in economics, and of course everything is controversial there, but it's quite obvious what these people do. They do something very systematic. I'm not talking about their success. I'm not saying anything about the success. I'm just saying if we look at the techniques that are used in science, then they are much more systematic than what we do in everyday life. And you'll find, of course, these things in economics, meteorology, material sciences, epidemiology. Wherever you look, a whole cosmos of systematic procedures opens. And these kinds of predictions are more orderly, more explicit, and better controlled than everyday predictions, independent of how successful they are in the end. Now, the systematicity in the defense of knowledge claims is almost trivial when I speak to philosophers of science, because it just means we take in science into account the fallibility of knowledge claims, and science can be then described in some sense as a systematic attempt at error elimination. This is what the scientists do, and they do that in very different forms. In the formal sciences, of course, it's a proof. If you state something that's not an axiom or a definition, then you've got to deliver a proof, otherwise it's not accepted. In the non-formal sciences, you have many, many different procedures that are based, many of them, on empirical data, and then you have strongly domain-specific procedures, what you do with these data, experiments, criticism of sources, and that's, of course, especially important because in the sciences we have to test theories because of their explanatory power. Therefore, we love theories, but they are always in principle speculative, and therefore we have to be extremely careful, and therefore we have a very, very, very high degree of sophistication in the defense of theories in the sciences because one knows that the possibility of error is very high when you talk theories. It's especially risky. Therefore, again, you should not be surprised that the procedures of trying to eliminate error are then very systematic in the sciences. And you have, in the historical disciplines, you can look in the natural histories, geology, paleontology, paleoceanography, or paleometeorology. You don't even know because you never had Wissenschaftskunde, right? I had to learn that, and you don't even know how many historical disciplines in the natural sciences exist. Paleoclimatology and so on. And they have, and also we have the historical disciplines in the humanities, political history, and art history, and so on. And it's always you have some sort of sources, right? Some remnants, physical remnants, and you look into them, and of course you want to build your story, your historical story on them, and you are very systematic in dealing with these sources, much more systematic than in our everyday stories when I claim, yes, I missed the tram because of that and that, then I tell you a story and I tell something, you know, and the sciences have to be more systematic here. Then this is just a little remark that quantified statements admit, of course, of more severe testing procedures. That's another argument why in science quantitative statements and other form, of course, of mathematized statements are desirable, because you can give a story for that within systematicity theory, because you have better testing procedures, more severe testing procedures for quantitative statements. All right. Now, critical discourse is a different category, different from the others, because it does not concern scientific knowledge itself. It concerns the social organization of knowledge. But also there we find systematicity in the following sense. There are countless social institutions that systematically foster critical discourse in science. Invited talks with discussion periods. Here I am. I know that you're going to ask me questions, right, and criticize me later. That's part of the game. Conferences, refereeings of papers and books, reviews of books, etc., etc., etc. Thousands of things where systematically the critical discussion is fostered. And many of these institutional forms are already practiced in science education. That's also in order to socialize people, that they are used to live in such a system of critical discourse that's highly systematized. Now, epistemic connectedness is a category here that I introduced. And that is unfortunately not so easy to explain because it has the same character as a concept like systematicity or refinement. I cannot tell you very much on an abstract level, and I must go into context and then I can tell you something, and then you only after the context you may see, oh, it makes sense to have this abstract term, although in abstract terms itself I cannot say very much about it. Now, abstractly it means all sorts of things: logical epistemic relations, logical dependency, confirmation, generalization, or citation even. Yes, you wonder which relations are meant, depends on the context, and the purpose is to distinguish, for instance, what I mentioned in the beginning, to distinguish product development from applied research, for instance, regarding automobile engines or chocolate research. I told you that there is this product development side with a transition area to research. Automobile engines, for instance, is something where I looked into it. When you look at the research pages then of Mercedes-Benz and you look at where they describe the new development of new products, the difference is that the scientific side has many more possible applications, and therefore it has a higher degree of epistemic connectedness. Whereas the knowledge you gain, it's also systematic what you do here when engineers, for instance, improve the new S-Class Mercedes engine. I mean, you all wait for the next model because you want to buy it next year. You work at a university, you want to come with your Mercedes S-Class, and you wait for the next model. You have to change it every year, otherwise it looks, old-fashioned. And what the engineers do there, they play around with the engine and they say it must be 10% less consumption. They play around with it. That doesn't lead to patents usually, but the firms know it has very little further application. So the epistemic connectedness of knowledge that is gained in product development is much lower than the knowledge that is in applied research. For instance, when people try to devise new designs, right, for combustion engines. So you have the same here. So this is a question more or less of generality, but we have other sciences as well where this generality aspect is not the case. But we have something similar, and the case I looked at is the difference between political journalism and contemporary history. Imagine you take the Süddeutsche Zeitung or another quality newspaper in order to be informed about the latest development in Afghanistan over the last 2 months, right? So you get something there from a journalist. What did this journalist do? Well, he researched, he talked to people, he talked to government officials, and so on and so forth. Now, if you look in a journal of contemporary history, say, of the Eastern countries there, that region of the world, you find a contemporary historians who did not do very much different than the journalist. He just did the same. What's the difference between the journal, the newspaper article and that one? The content may be more or less the same. What's the difference? Footnotes, right? You have tons of footnotes here and no footnote here. What is a footnote? Epistemic connections, right? That the footnotes tell you, they connect what is in the text with different sources, with comparisons to other countries, with whatnot, right? So the difference here between, although the content is the same, and I have one particular example about the role of football in Lebanon, by the same author, and I have the article is in the Frankfurter Allgemeine, and the article is on, I forgot the journal, and it's really the difference is footnotes, and that is this does not belong to science, that does belong to science, and what you see here is that contemporary history has a higher degree of epistemic connectedness, and of course epistemic connectedness has something to do with being systematic, and therefore I need this category here in order to make these, of course, gliding differences. All right, that's what I said, okay? Then in the sciences there is an ideal of completeness, which is of course also an aspect of being systematic. The strong and steady increase of knowledge is one of the principal differences between Western science, especially from the 17th century on, and other kinds of knowledge. And if one asks, why is that? What is going on here? Then one of the reasons is a motivation or institutional goal, or however one calls that, which is a little tricky, is that there is an ideal of completeness with respect to the domain in question. And that is a property of science. And again, I mean, it's very simple. The completeness of axiomatic system, of course, only as far as completeness goes in mathematics, as we had to learn. Of course, the periodic system of elements has to be complete. The fundamental interactions in physics, one wants to have all of them. the classification of biological species, the division of processes into periods, the critical complete additions. Everywhere you'll see people want to have completeness, at least more completeness than in the corresponding everyday practices. But it's not only that we have this ideal in which systematicity plays a role, but it is also in the realization of this ideal, namely the knowledge generation, and there you find, of course, it's almost trivial, many different systematic ways to achieve knowledge. Systematic search for new or improved data happens both in the humanities, in the social sciences, in the natural sciences, in the engineering sciences, also in the formal sciences to some degree, archives, measurement, observations, systematic closing of knowledge gaps on the basis of existing knowledge. That is, so to speak, a part of my counter answer against scientific method. Science is an autocatalytic process, or if you prefer the electro-engineering's talk, it's self-amplifying. This is for the chemists, this is for the engineers. Science is building on the existing knowledge and is not done by rules. And by the way, what you get, of course, for you, if you are mathematically, if you've got infinite resources, you get immediately, of course, exponential growth of science, and that is what we had seen in the history from the 17th century on. So we get, by this idea that the systematic knowledge generation on the basis of what you already know is the trick why you can also understand why, under certain conditions, this is exponential growth that we have seen. Now, also something extremely systematic which is done in the science is the exploitation of other domains of knowledge, especially of technology. Within the last 50 years, a large number of disciplines have turned completely different due to computers. I mean, there are many areas now that are science which weren't science before, and computers, I mean, you know, that are everywhere, and that's systematically done. Also, if you look also in the humanities, you find these chronology techniques by radiocarbon methods and whatnot everywhere. People try to get everything they can get, every technology, every other domains of knowledge, in order to increase the capability of knowledge generation. It's extremely systematic what's happening there. And we have even something, sounds paradoxical, it's the systematic exploitation of chance, namely by brute force approaches and explorative experimentation, where you can make chance discoveries, or this is a third category here, brute force approaches, which you find, of course, for instance, in pharmacology, that people then use literally hundreds of thousands of variation of a certain compound and test it for biological effects. And that's the way how you can produce new drugs in the longer run. Explorative experimentation is the same. You know, you play around with the system. It's done, say, in physiology. It's less done on the LHC in physics, but explorative experimentation in the life science is something very important. When you don't know anything or almost nothing of a system, then you play around with it, you know, and look what is happening, and then suddenly something happening that leads to the formulation of some law or something. Okay, and also chance discoveries during tests of hypothesis. This is also something which is, so to speak, inbuilt into the scientific process, that you test hypothesis and something else happens, right? You make a chance discovery. And this is also all systematically interwoven with the activity of science. Now, the structure and representation of knowledge is also something, also it's, you know, you can feel books about that. When you look how the sciences do that, again, the formal sciences, it's very simple. You have an axiomatic representation of a scientific area. It's quite clear. You write down the axioms and the definitions, and then you write down the theorems and the proofs, and here you see this is the whole body of knowledge. And you find in the non-formal sciences many different ways how to do that. Let me only look at one particular thing. If you look at special forms of representation, nomenclature, for instance, I looked quite closely into the systems of chemical nomenclature. You find just the introductions for the introductions to the books for chemical nomenclature have more than 300 pages, right? Only the introduction in order to understand the nomenclature. Remember, we're talking 60 million chemical compounds, and you've got to have funny names for them. You can also have that in geography, by the way. There's a system, geographical information system about the United States of America, and that has 2 million items. Geographical items to describe America, the continent of America. You've got to have a naming system for that, right? It's not just Aunt Mary and Uncle Hans, and you need a few names. You must be much more systematic, and this is what the sciences are in the representation of knowledge. So it's, again, it's pretty obvious. Okay, I have Wi-Fi, thank you. And this is just a remark that the systematic representations increases the efficiency of knowledge reception, and it supports error elimination and knowledge gap diagnosis. In one word or in one sentence, we have positive feedback between different aspects of systematicity. So it's not just these 9 dimensions of systematicity, but they are also interwoven and increase each other. It's positive feedback effects. Okay, this was a little of the material that I wanted to show you, and that is the justification of the answer, namely by simply showing you by select examples that indeed the sciences are in these 9 dimensions, and from all fields of learning, including the humanities, are really much more systematic. Now, the comparison with other positions has the following argumentative idea, namely a heuristic thesis, that the earlier explanation of what science is were not just mistaken. I'm not saying, look, Kant and Aristotle, oh, sorry, all wrong. No, they were one-sided, right? And what I'm doing here, systematicity theory, is a generalization of everything that was useful about science, you know, all the philosophical theories about science of the last 2,500 years. And I'm showing you why systematicity theory is a generalization. Again, I don't have enough time to do that in detail. We start, of course, with Aristotle. And in Aristotle, the ideal of science that he at least explicitly developed was what can be called the categorical deductive ideal of science, exemplified by Euclidean geometry, which is, of course, not an accident because Euclidean geometry was composed roughly at the same time. And I mean, it's a wonderful case of systematicity. I really bought the 3 volumes now. There's a wonderful edition of Euclidean geometry. And I'm fascinated what the Greeks did within 300 years, because they started 600 before Christ and 300 that appeared. And it's just incredible. I mean, this Euclidean geometry developed there. I mean, it's breathtaking, and it's really systematic. Really, I mean, the book was a textbook for something like 2,100 years. It was still used in the 19th century as a textbook, right? And it was a model for many, many other disciplines. This was the model of real science, right? And of course, it's extremely systematic, no doubt. But it is, of course, a very special form of systematicity that is embodied there, namely, the systematicity is especially emphasized regarding the defense of knowledge claims and regarding the structure and representation of knowledge. And the other dimensions aren't that strong in there, and it's a very particular form of systematicity, namely, defense of knowledge claims must be a proof. That's a very specific form of defense of knowledge claim. And I'm saying, well, there are other forms in other sciences. So it's a very nice one, very convincing case, but a special case of systematicity theory. And we need more general stuff because... Now, here's another one. Descartes, of course, he would be the great enemy because Descartes says, no, methodicity is all there is to science, right? Now, let's look. He's the key witness for the idea of method as an adequate means for the explication of science. There were other people as well, but he's really the most important one. Now, here are the 4 rules of methods that you find in the Discours de la méthode, which is only an introduction to the scientific work, so never forget that, please. Okay, here's the first one: to accept as truth only if something is evident, to dissolve problems into smaller problems, to think in adequate order, and to strive for completeness. Now, if you map that onto the 9 dimensions, it's very simple that 2 rules are part of a heuristics, to resolve problems into smaller problems, of a rational heuristics, and to think in adequate order. These are rules of rational heuristics, and we wouldn't necessarily accept them. So what we should accept is, well, not exactly what he says, to accept as truth only if something is evident, or to strive for completeness, but what you see here is dimension 4, right, to accept as truth. He says, okay, you've got to defend knowledge claims, and you must use evidence, right, being evident. That's a particular form of systematic defense of knowledge claims. And to strive for completeness, well, that's the same what I said. I took two different forms of completeness, namely the completeness of knowledge as the body and the completeness of the strive to completeness in dimension 8. So this can be really nicely subsumed, and this is just really special cases. Now another one is here. In general, that's my general story. Methodicity is a special case of systematicity. Everything that's methodical is systematic, but not everything that's systematic is methodical, because the methodical has this time idea in it, and that's not necessarily a part of systematicity. Now we have other people here. Kant, of course, he already appears to be a defender of systematicity. It's much more complicated when one looks closely at it, but I'm giving you the simple story. The systematic unity of what transforms common knowledge into science. Okay, this is what you know from German philosophy. It's all already in Kant. Of course, you can't say anything new. Oh, yeah. Well, if one looks a little closer, then of course you see that Kant has a very specific and narrow notion of systematicity. It's much narrower. He's a wonderful special case, again, of systematicity theory. It concerns only the structure and representation of knowledge and is understood in the restricted sense of axiomatization, roughly speaking. That's not the full story, but roughly speaking. So Kant is okay. I mean, the sciences were much, much less developed at his times as they are today, and this was a nice theory for the sciences of his day, but today we got to say, no, it doesn't fit. I mean, there were no humanities in Kant's times in our sense today, so he couldn't cover them, and we have to cover them. All right, then we have, and that's again very rough, logical empiricism and Popper. If you look at their main topics, then they did, of course, where in this field where I'm moving as well, it's the discussion of the role of observation, of protocol sentences, and of inductive confirmation or deductive falsification of hypotheses, and it's of course scientific explanation and prediction, and it's quite obvious that the main thrust is systematicity regarding the defense of knowledge claims, explanation and prediction. You find very little about description, for instance, very little about general ideas about classification, very little about the dynamics of science. In Popper you find that less in logical empiricism, and it all fits nicely into the larger picture that is given by systematicity theory. And here we have Feyerabend, and Feyerabend should be my real enemy, because apparently Feyerabend is in against method and also in other writings an enemy of methodicity and systematicity by saying anything goes. Don't misunderstand, anything goes, but in general it seems to be an opponent of systematicity and methodicity. And historically it's the case that it was really my idea about this project was really triggered by Feyerabend's works, because I thought, well, Feyerabend, you try to show that science is nothing special, has no special characteristic. Your argument is a fallacy that you bring. The argument the argument is really a logical fallacy. He mistakes a necessary condition for a sufficient one, sufficient for a necessary one, which is unfortunate. You know, he says, from methodicity it follows that science is special. We have no methodicity, therefore science is not special. That's his argument. That's a fallacy. It took me 20 years to discover that. So don't worry, if you didn't discover it, get yourself another 10 years. Or just listen. Okay, so he seems to be here an opponent, and he was my enemy, and what do I do with him? Here are even more clear statements. Science has no common structure. Well, if he's right, I'm dead. No, perhaps not. Or science is a collage, not a system. Here we go. Now, Feyerabend opposes a common structure of science in terms of necessary and sufficient conditions. In the architecture of my project, suggested by an analysis of what systematicity is of course not this rigid structure, but this Wittgensteinian network. And therefore, Feyerabend is no problem. Here in systematicity theory, the unity of science is constituted by a net of family resemblance relations among different concepts of systematicity. It's therefore very weak. You may even say it's disunity of science. Well, perhaps, whatever. But it's certainly so that I'm, so to speak, undermining Feyerabend's, or not undermining, but I'm simply avoiding his opposition because he's too strong, and I'm just making something weaker so he can be a friend here as well. And here is the summary. Albert Einstein is always given for any talk, either in German or English. To end with Albert Einstein is wonderful, right? Especially in Munich then. Oh, he wasn't in Munich, was he? No, he wasn't really. at any rate. But he certainly liked Munich, I guess. Yeah. He knew the Sommerfeld School and so on. Okay, here's Albert Einstein, 1936. The whole of science is nothing but a refinement of everyday thinking. Okay, and now you are, of course, already sensible and sensitive. What does refinement mean in this context? We don't know. Now, here's my suggestion. The whole of science is nothing but a systematization of everyday thinking, and you find even one particular locus in one paper where he says something very similar to that. Thank you very much.
Thanks a lot.